This is problem 7 on page 79, and it looked like a good mix of trigonometry and exponential functions. But I'm kind of amazed because it is the first typographical error I've ever found in this book. And so let's read the problem. It's parentheses e to the x sine y plus e to the minus y dx minus x e to the minus y minus e to the x cosine y. They put dy here, but really dy belongs outside the parentheses, so there's the typographical error. It's the only error I've ever found in this book, which is pretty amazing. There's probably a few others, but they're not easy to locate. Alright, so now it's obviously not a linear coefficient problem, and I would say it's not a homogeneous problem either. So doing our substitution, u equal y over x, is just not going to pan out here at all for us. So next thing to check is this an exact differential equation? So remember that this is, let me go through the technique again. What happens is we think of this as p dx plus q dy equal to 0. And if the partial of p with respect to y, sorry I got that wrong here, let's make that a y, is equal to partial q with respect to x, then it's exact. And then we find the solution. The solution is z equal to constant, where partial of z with respect to x equals to p, and z with respect to y is equal to q. Alright, and we get the solution by integrating these terms. So again, in order to qualify as an exact differential equation, we have to verify that the second marked mixed partial derivatives of this hypothetical function z are equal. If they're not, then they do not come from a function z. It's not an exact differential equation. So we have to verify that to show this exact differential equation. Then we can finish it by doing some integrations. So that's the idea there. Okay, well, let's check it out then. First I'm going to take this partial derivative with respect to y. So partial with respect to y of e to the x sine y plus e to the minus y will be, okay, so we're treating x as the constant and y as the variable. So derivative of y here is going to be cosine of y, e to the x cosine y, and then minus e to the negative y. Now we'll take the partial with respect to x of q, and q, really we need this negative sign here, so it's going to be negative x e to the minus y plus e to the x cosine y. I'm not sure why the book wrote it the way they did, but we can work around that. Alright, so partial with respect to x, we treat the y as a constant, take derivative with respect to x, so I have minus 1 times e to the negative y, so this is equal to minus e to the negative y. And then with respect to x, derivative of e to the x is e to the x, so I have e to the x times our constant cosine y plus e to the x cosine y. So as you can see, these are both equal. So this is indeed an exact differential equation. Again, I want to point out that this has a role in vector calculus in relation to conservative force fields, which is kind of interesting. Alright, so we verified that it's an exact differential equation, which means I can confidently go about solving. So I really don't need that anymore. That was just to verify that it's exact. It identified this particular type of differential equation. And so my function z will be the integral of e to the x sine y plus e to the minus y dx. So I integrate this with respect to x. And again, it's one of these funny integrals that you don't face in ordinary calculus. You're not supposed to integrate with two variables in calculus when you have a single integral. But it's a partial integration. We're going to treat, because we're doing with respect to x, we're going to treat y as a constant. So, integrate e to the x, we'll get e to the x sine y plus, this is a constant, so when I integrate with respect to x, I'll get x e to the minus y plus my additive constant, my plus c, so to speak, is a function of y, and traditionally we call it g of y. Alright, now we take the partial of z with respect to y and match it up to q. And so when I take this partial respect to y, I'm treating x as a constant. So this derivative is going to be cosine y. So e to the x cosine y. E to the x cosine y. Alright. And then we have this derivative of e to the minus y is negative e to the minus y times x. So it's minus x e to the minus y plus g prime of y. Okay, let me see. Now, up here, I have negative x e to the minus x, negative x e to the minus y. Okay, that equals, and e to the x cosine y. These two negatives cancel. That's a positive. That equals, and there's nothing corresponding here for g. So g prime of y, in this case, is 0, which means g of y is a constant. Well, since the solution of my problem is z equal to a constant, this constant is going to be absorbed into the solution constant. So I really don't have to worry about this at all. It gets absorbed because, again, the solution to dz equal to 0 is z equal to a constant when I integrate. So this constant gets absorbed over here. We don't have to worry about it. So we have an answer then. My solution is going to be this part, that's 0, equal to a constant. So let me write that out. There's our solution. E to the x sine y plus x e to the minus y equals to the constant. Alright, so we could check it like I did the last problem, or we could just look in the back of the book here, or the answer is e to the x sine y plus x e to the minus y equal to constant. There we go. So that's correct. Alright, I'll do one more of these.